In this fifth lecture on magnetic field in material medium, today we shall mainly focus on the H field. Let us first write this equation: curl B is equal to mu 0 J. It is the differential form of Ampere Circuital law. But we found here that the J is composed of two parts. One is the conduction current density, another one is the magnetization current density. This is the conduction current density and this is the magnetization current density. And furthermore, we know that Jm Jm is the curl of M. So we write here this equation as curl of mu 0 B minus M is equal to Jc. So we see that this, if we introduce a quantity H field, then H field is simply Jc, where H field is defined as 1 upon mu 0 B minus M, or B is equal to mu 0 H plus M. This is the H field. It is an auxiliary field which has been introduced so that the curl of this field is the conduction current density. In general, what happens that we know the conduction current density because we create it in laboratory, and we can measure the current that we are sending through the apparatus through a meter. So we know Jc, so we can find out H from it by applying Ampere Circuital law, that is H dot dr over a closed path is equal to Jc dot ds, where S is the surface bounded by the contour C, and it is the conduction current enclosed. So this enables us to find out H, the auxiliary field. This H field is similar to the D field introduced in case of electrostatics. We know that in electrostatics the Gauss's divergence theorem is this, and divergence of D is related to rho C. So if you know the conduction charge density, then we can set up this equation. And here the case is similar. If we know the conduction current density, then we can set this equation. One thing is that since for electrostatic field curl E is 0, it provides a complete description, but here the H field is not completely specified, because if you want to specify a vector field, then we must provide its source and circulation. It provides the circulation, but the source, that is to say, if we want to specify a vector field uniquely, one must provide its knowledge about its curl and divergence. The knowledge of curl is given, but that means we know that divergence B is 0, that is mu 0 times divergence of H plus M is 0, that leads you that divergence of H is equal to minus divergence of M. Since M is not known to us beforehand, the curl of H is not divergence of H is not known, so H is not specified for completely. This is sometimes called the deceptive parallels. One thing more, I want to remind you the corresponding definition in the case of electrostatics. In electrostatics, D field is defined as mu 0 E times P. Mark the difference here, mu 0 is multiplied with M, but there is no epsilon 0 multiplied with P. This is the difference, and that is to say H and M has the same dimension, but P and E do not have the same dimension. Let us look at so H is an auxiliary field which is introduced, which facilitates calculation. Let us consider a magnetic material or a conductor made up of a magnetic material which carries a conduction current density in the Z direction. The conduction current density is provided by some J0 K cap. So we know that if we apply Ampere Circuital law, we know that the field H1, that is H for rho less than R is the radius, the field is proportional to rho, and H2, the field for rho greater than R, is proportional to 1 by rho. The detailed factor can be calculated. The thing is that we know the H field at internal point as well as at external point. We call one as the internal point, two as the external point. Since this is placed in this conductor is placed in vacuum, we know that M2 is 0, corresponding M2 is 0, so B2 is known. So the B field, magnetic induction field, is known at an external point. But since it is a magnetized material, we do not know M1 here right now, so B is not known. But H can be calculated very easily. That is the utility of introducing H field. Such an auxiliary field D has been introduced in electrostatics, but if we consider the utility purpose, D field is not that much popular in experiments to the experimentalist as H is, because H, to know H, one need to know current. The current can be measured very easily, so we go we use this, or one prefers to use H field to H field for the calculation purpose. But if you want to know D field in reality, then you need to know charge density. It is easier to know charge potential difference rather than charge density. So D is not prepared in laboratory as H is. We shall now come to this definition or this justification for the introduction of H field in another way. Another alternative justification, we are looking for another alternative justification for the H field. If we recall that the magnetic vector potential approach, is that the magnetic vector potential at a field point R is given by mu 0 upon 4 pi. First, the volume distribution. where Jm and Jms are related to curls of M. So Jm is equal to curl of M and Jms is equal to M cross N cap. Now if we want to find out the field from there, two curl operations are involved. One curl operation is this, which enables one to know Jm. Another curl operation will be needed to get B from Am, because Bm is equal to curl of Am. So two curl operations are involved, and it is not always easy to perform curl operation in reality. So what do? We look for a alternative scalar approach. If we could bypass this complicated calculation involving curl by introducing some suitable scalar quantity. To this end, we recall that we came to this expression starting from the fact that this dv. This was the starting expression which led to this expression. We are actually interested about Bm. To calculate Bm, we introduce the scalar potential and then taking the vector potential and then taking the curl of it, we could arrive at B. Instead, we could take the curl of this expression to get the B. In this approach, we are not interested about getting an expression for vector potential, because our aim is to know B. So we write Bm is equal to curl of M, and we take the curl of this expression. So this is mu0 upon 4 pi. Notice that these are the integration over source coordinate, and curl is over the field coordinate. So we interchange this, as we have done these things many times earlier, so I am skipping steps. So this comes out to be curl of M r prime cross r by r cubed. You note that it is a differentiation with respect to field coordinate, and it is a function of source coordinate, so it doesn't work on it, it works on it. The next part, so this becomes if we use back curve rule with proper care that nabla operates on this part, not on this, we get this part is simply 4 pi times delta of r. So we write it as mu0 upon 4 pi, then first part is 4 pi m at r prime. Delta r means delta of r minus r prime. Then this part. This combination operating on r by r cube dv prime, integration over pi prime. If we do this part is 4 pi cancels out. This is mu 0 m at the field point, no prime, it is m at the field point, it is field coordinate. We have used the property of delta function, that integration f of x prime delta x minus x prime integrated over x prime whole space. This is f of x. This is the property. This property has been used in 3 dimensions. Now come to this term. Before coming to this, let us write that this is minus mu 0 upon 4 pi times this part. We recall that m at r prime cross curl of r upon r cube. Since it is radial, this is 0 identically. But if we apply the vector identity, we get 2 terms. One is that this will come out and there will be some dot on this. This is the first term, and second term is this. This is the term that we have here. So in all other words, we call m of r prime dot nabla operating on r upon r cube is equal to let me again. This is 0 we know, but we use the vector identity, so we get 2 terms, of which this term matches with the integrand that we left, and so this integrand can be written as this minus mu 0, then for integration over v prime gradient of So in coming to this step, we have replaced this part by this one. This is the thing that we have done. Now, this part can be written as mu 0 m at r minus this part is taken outside, so we write mu 0 delta phi m at r, where phi m of r is defined as 1 upon 4 pi, because mu 0 is taken there, so 1 by 4 pi is there, and divergence is taken out, so this is m r prime dot r by r cube over integrated over V prime. This is nothing but the usual magnetic scalar potential, which can be written as 1 by 4 pi that we have obtained earlier. So we see that the magnetic field at an external point due to magnetized material can be considered to be composed of two parts. One is the arising from the magnetization itself, another part arising from the scalar potential that we have argued earlier. So if we want to calculate what is the total field at an external point, so if we want to find out total field at an external point, we must first describe the geometry of the problem. Consider the geometry of the problem first. We have a conduction charges. We have conduction charges. Conduction charges which are bound within volume Vc and surface Sc bounded by a conductor and having the conduction current density Jc. And we have a magnetic material. Situated in the neighborhood. It is a magnetic material. Which is within volume V prime bounded by the surface S prime. And our aim is to find out field at point P. So field at point P will have two contributions. One directly coming from there. So if we call field at P is equal to field due to the conduction charges plus field due to the bound or magnetization charges. So this part is mu0 upon 4 pi Now let me introduce the coordinate system. This coordinate is prime, r prime. As usual, we denote it by r prime, and so this is prime coordinate. This is called RC coordinate. This is R coordinate. So that this is capital RC, which is R minus RC, and this is capital R. Capital R is equal to R minus R prime. And this is the suitably chosen origin. So this is RC cross capital RC by RC cubed dVc over Vc. This is the contribution of this, and for the contribution of the rest of the material we use this expression. Note that it is at R. Mu0 part is missing. If we write it phi m in longhand, then we have this expression. So let me first write it and now come to the conclusion. rho m at r prime by r in principle, we can find out B, the left hand side we will show the B, the total field at R, provided we know JC and M, because these two quantities are related to M's and the geometries, and we assume that the geometry is known, so we could find out the B can be obtained if JC and M are known, but M at R prime is related to B at R prime, because the magnetization that is produced at a point depends on the total field acting on it. It comprises of the external field, the field due to the conduction current plus the local field. So what we get an integral equation in B, that is B to be known appears within the integration. So the equation is of this sort: y as a function of x is some integral of at x is y at x prime and other things, there are other things, and integrated over x prime. This is the expression. And there is another function, say f of x prime, and so this is an integral equation. So we get an integral equation which is not very easy to solve at all. So what we do, we keeping this term, we recombine these two to call a new field. So we call this, or we write this as mu 0 m plus mu 0 h, where h at R is the mu 0 term will not be there. Note the change. At first sight, it seems that we have gained nothing. Just we have introduced the H field, but if we take the curl of this field, this part goes and this leads to JC. So this is the equation that we obtained earlier. So we want to emphasize that the B field at a point is maybe thought of to made up of two parts. One is directly related to the magnetization at R at the field point, plus something which arises due to the conduction current and the magnetization pole densities. So H field, in that sense, H does not depend only on conduction current. H depends as well as on the magnetization charge densities, but curl of H is independent of this part. That is why we say that this curl of H is equal to JC does not specify H completely, and to specify H completely one must also specify divergence of H, and which then gives an additional term in the expression of H.